You know, I'm sorry, but I forgot to start the recording again. I had it paused when we started up. So the recording is going to start in the middle here. Apologies for that. This is all in the notes. Oh, rats. All I can say, read the notes and try to remember what we've just done.
Dr. Wheeler.
Yes.
I'm recording it too through my screen capture because it gives better resolution than
good.
the recording, so I can see the board better when I watch it. But
okay,
anyways, I'll put it on YouTube and share it if anybody wants the link.
Fabulous. Okay, guys. Check with Lyle. He's got it. Good. Okay. So let's try another with 4 gamma matrices. So what I want to do is I'm going to rewrite this in terms of itself. I'm going to move one of these all the way through, then use the cyclic property of the trace. So I do it a step at a time. Gamma mu is minus gamma mu, unless they're the same, in which case I pick up 2 times the identity, like that. And I'll just leave the identity matrix understood here. So now this is the trace of, all right, I'm bringing gamma nu through. So I get 2 things here, right? I have gamma alpha. Now I'm going to flip these next 2. So I'll end up with plus gamma nu, gamma beta, minus 2 eta nu beta, and then that gamma mu. That's the first term where I've flipped these 2, plus 2 eta mu nu times the trace of gamma alpha gamma beta. Okay, everybody with me here? So now I get 2 terms from this one. I want to bring that gamma nu past the gamma alpha. So I'm going to have a trace. So the first term, I still have 4 in this first term. I'm going to have minus gamma nu, gamma alpha, gamma beta, gamma mu, and then plus 2 eta alpha nu, gamma beta, gamma mu. That's this term. Let's see. Yeah, that's all from this first term. Then we have minus 2 eta nu beta trace gamma alpha gamma mu, and then this trace we've already done. That's going to be 4 times eta. So this becomes 8 times eta mu nu times eta alpha beta for that last one. Now, this first one is the same as the original thing, except it's got a minus sign. Because I can now bring gamma nu to the tail end, and I'm back where I started. So here I have minus the original trace. I bring it to this side and I get 2 of them. 2 trace of gamma alpha, gamma beta, gamma mu, gamma nu, and it's equal to whatever's left over here. And putting in the traces of these products, which we've already done, I'm going to get an overall 8. Then I have eta alpha nu, eta beta mu from this one, minus eta nu beta, eta alpha mu from this one, plus eta mu nu, eta alpha beta from the last one, and then canceling the 2 gives me 4, and I've got my trace. So it's a sum of 3 different, it's 4 times the sum difference of 3 different permutations of the indices on etas. And that's the trace of 4 gamma matrices. 6, you can see you've got a lot more steps. The more you have to take the trace of, the more things you commute through. And ultimately, you're going to reduce it to traces you've already done. So exercise for homework, do 6, right? What's the trace of 6 gamma matrices? I don't know if I actually wrote that with the in the notes, but go ahead, do that. It's good for you. All right. Let's see. Okay, we found the metrics. I'm just scrolling through the notes here again. So let's go back to the Dirac equation. I'm not going to solve the Dirac equation yet. It's not hard, but I want to quantize fields in order. So we're going to quantize scalar fields first, then we'll quantize the Dirac equation, then we'll quantize electromagnetism. And in that process, one of the things, the first thing you do is you solve the equation. So we're going to solve the vacuum Dirac equation completely as a, it'll be a Fourier series kind of thing. But then when we quantize it. For now, let's just look at the Dirac equation, the Dirac action, and the conjugate Dirac equation. That's brief.
Quick question for you.
Yeah.
What is that final last scribble in the very far right corner?
Oh,
bottom.
All right, here we go. Let's see. Final last. Yeah. Oh, what a good question. All right.
Is that an eta alpha beta?
These are all metric. This last term is eta mu nu times eta alpha beta.
That's what I had thought. I just wanted to be sure. Okay.
Yeah. Yeah. And now you know how to recalculate it yourself, right? So, but yeah, good question. Yeah, that was, I get down to that corner and it is a bit of a scrawl. Okay, so the Dirac equation, a little bit of notation here. I don't recall if we've talked about this yet, but all right, I gamma mu d dx mu minus m acting on psi is 0. That's the Dirac equation. But now we introduce this convention that, anytime I have any vector contracted on a gamma matrix, I just write that as v slash, right? Or the vector slash. So when I have gamma mu partial mu, I write that as the d with a slash. It's just a shorthand, just that, it's like the Einstein convention. It saves writing a lot of Greek things. So if you see a d slash, it means that. So we can equally well write this as I d slash minus m psi equals 0. That's the Dirac equation. So this is some first derivatives contracted into some matrices, all acting on a column vector equals 0. And, we actually do a plane wave solution to that and take a superposition of plane waves.
Quick question, Dr. Wheeler.
Yes.
I noticed that both of those that get the slash, one of them on the gamma matrix, the mu is down, the other is up. So is that something that we need to be not concerned about, but just conscious of that? I'm assuming there's a metric difference there, right?
Yeah, that's a Lorentz metric. So this follows the usual rules of space-time inner product. So this is the same as gamma up and a v down. It's the same as v down and gamma up. The usual rules apply here. That's just a real linear combination of gamma matrices using the Lorentzian inner product.
Okay.
Good. Any other questions? We're good? Okay. All right. Then an action for the Dirac equation and the conjugate of the Dirac equation. if I take a,
Hey, Professor, sorry, I do have a quick question, I guess.
yeah, uh-huh,
So and we got this from starting from the Klein-Gordon equation. So we went from a second order equation and then used our symmetry to reduce it to a first order one, right?
yeah,
So is
yeah,
that
that's,
why? So in some senses, I mean, we kind of took a square root of an operator, but did we do that like, yeah, is there some way where that's a general method where we have a higher order differential equation and we're trying to find a lower power, and so we've expanded the field so that we're certain that we can, it's like the fundamental theorem of algebra is what I'm digging.
let's see, well, let's see, I don't think that when Direct did this, that there was any guarantee that it would work, except that there really should be a linear relativistic equation for a field theory. But having done it once, that's enough, right? We found that this does imply the Klein-Gordon equation if we whack it with its conjugate or something, and if these gammas satisfy the Clifford algebra. Well, they do now. They satisfy the Clifford algebra. That property is implicit in this, but now this is our new field theory. This is a linear relativistic wave equation for something, for a spinner, for a complex four vector. That's certainly what it is, but it's relativistic. We can show, we can find a non-relativistic limit of this that reproduces the Schrodinger equation, in fact, with a bit of work. We don't have to do that here. I don't know. Yeah, maybe those YouTube videos go through that. But this is a relativistic version of the Schrodinger equation. Now, suppose we try to write an action for this. Well, it's natural enough because we want the action to be real to multiply by the conjugate spinner here. And we sandwich this, and we're pretty close because if I vary the conjugate spinner, and I think have you guys worked with the complex Klein-Gordon equation? We'll do that probably for homework even, but you can vary the field and its complex conjugate independently. You don't have to separate into real and imaginary parts and vary those. You can just vary phi and phi star. Well, here you can vary psi and psi dagger independently, and the results are correct. So here, varying psi dagger, boom, we've got the Dirac equation. That was easy. If I vary psi, then I integrate by parts on this term, and that looks pretty good, but yeah, there's one thing wrong here. The problem is this Lagrangian is not real. And if your Lagrangian is not real, then the complex conjugate of your field equation is not the same as what you get when you vary the field and get a complex equation, and your fields are overdetermined. You get two different equations for the conjugate. So you need a real action. And let's see what happens if I take the dagger of this. The problem is in those gamma matrices. The dagger of that is, okay, we get a psi dagger first. Then we have, well, minus I. And then let's write this explicitly. Gamma mu dagger d mu, that's the d slash minus m. And psi dagger dagger is just psi, but this, this is plus or minus I gamma mu. So that sign is messing us up. This is why we need the metric. We need an H in here. And as I've said, the metric is actually gamma 0. So we're going to put a gamma 0 in here. Now it's real. So let's check it again. Now, gamma 0 is really H, but we're abusing notation because everyone does, as long as we know we're doing it. So now let's take the dagger of this thing. So I have psi dagger, then we're going to have minus I gamma mu dagger d mu minus m gamma 0 dagger psi. So this is L dagger, if I call this thing L, Lagrange density. Oh, yeah, this is a field. We are integrating. This is a Lagrange density. We're integrating V4X here. Now, we need a minus sign. Here's the gamma 0. So this term, gamma 0 dagger is equal to gamma 0. So on the M term, it just comes through and sits here. Now we have to worry about I gamma mu dagger gamma 0 and ask what happens here. So there are two cases. If let's see, I'm worrying about the cases now. Let's see, that I is bothering me. All right, if we have gamma I dagger gamma 0, gamma I dagger, yeah, I wonder if we don't want that I in there. Let's try it without the I. It depends on your basis whether you need an I there or not. I'm worrying that we don't need an I. Let's not have an I for the moment. Then this is minus gamma I gamma 0, but those anti-commute, so this is plus gamma 0 gamma I. If we have a gamma 0 dagger gamma 0, that's gamma 0 gamma 0, and we don't have to commute anything. That puts the gamma 0 on the right. So this Lagrangian, let's see, I'm surprised I don't need the I there, but the math doesn't lie. So here we go. So with this gamma 0 here, this turns into psi dagger. The gamma 0 comes through, changing that to a regular gamma 0, and we're back to our original. So we don't need the I there. We would need the I if we had chosen the other metric. If gamma 0 dagger, if gamma 0 was anti-Hermitian, then we would have had gamma 0 dagger being minus gamma 0, and we would need the I. So whether you need the I depends on the signature you choose for the Lorentz metric, and we've chosen one that I'm not used to using. So it looks like we do not need the I in order for this action to be real. So now this is a real action, and because we need this metric in here, we write the dual vector as psi bar. So we're finding psi bar if we're not abusing the notation, it's psi bar h, and we'll often write that as psi bar gamma 0. So now we have d slash minus m psi as the Dirac action. So that's real. So we have consistency between what we get when we vary psi, the other field equation, the other version of the Dirac equation, and what we get when we take the complex conjugate of this Dirac equation. So let's see what happens.
So Professor?
Yeah.
Is this like we have a different basis, like a non-canonical basis for the dual space, and this bar is representing like how we want what our dual space basis actually should be? In the inner product.
Sorry, I have a question. If I put in indices here, psi dagger is an up thing, H is my AB. So, this is psi bar, but it's got an index down. It's a true dual vector.
Mm-hmm.
All right. So does
That's
that
a
answer?
dual
Yep.
with respect to the Hermitian inner product, right?
Yeah, that's what I'm trying to say.
I'm sure that.
We have a different bilinear form. We don't just have the straight Omicron deltas. H isn't the identity. So it's with respect to a different. We have a dual base with respect to a different bilinear form, right? Like.
Okay. H is a Hermitian spinor metric.
Yeah. Uh-huh.
Right.
It's like the spin metric. It's like only for the inner product on the spinor space, right?
These comments are a hoot. Sorry. Yeah, that's right. If something doesn't work, erase it. Good. You sometimes see the Dirac equation with the I, sometimes without, and it depends on what basis you choose for your gamma matrices, and it depends on what form of the metric you choose. And I have chosen one of those differently than what I thought, so that's why I had to erase the I. Let's see, or yes, by inspection. Some things you can do by inspection. Now I'm not sure whether I've gotten to your question, Alex.
Yeah, I guess I'm just saying, like, there's like two types of raising we can do. Like, you can do the metric to be upper or lower, and then we have this inner product on the spinor space that we can be dual to. And these bars are the dual on the inner product space.
That's right. Yes, that's right. We have two spaces, right? We have space-time, and we have this vector space of spinors, and each of them has dual vectors and metrics. Right.
Thank you.
Yeah, you're welcome. So let's vary the fields now that we've got a real action and see what happens. So if I vary psi dagger in S, you don't have to integrate anything by parts. You immediately see, and in fact, we can do better. We can vary psi bar. No harm in doing that. There's still independent degrees of freedom of the unconjugated psi. So all of this is psi bar here. It's not here. And we just get d slash minus m psi equals 0. That is the Dirac equation in our basis and metric signature. If we vary psi and set that to 0, we have to be a little more careful. So we have psi bar d slash minus m del psi d4x. Now, here we have a derivative of the variation, so we do have to integrate by parts. So let's write this out a little more carefully, or in a little more detail. We have psi bar gamma mu d mu del psi in the first term, and minus psi bar times m del psi in the second, all integrated d4x. Now we integrate by parts here, so this one becomes minus d mu. We drop the surface term. We have a d mu of psi bar contracted on a gamma mu, and now we can pull out the variation of psi. So we get the opposite sign, which let's put it up here. Then we can cancel the minus sign, and we have d mu psi gamma mu minus m psi. This is bar. Sorry, bar equals plus equals 0. So it changes the relative sign. Now we cannot write this as d slash because the gamma is multiplying this vector on the right. we can't move that gamma mu over here and call that d slash. What we do is we write a d slash this way with an arrow to tell us that the derivative is acting here. And this is, again, this is standard notation for the conjugate Dirac equation. So this is the conjugate Dirac equation, and then the regular Dirac equation, d slash minus m psi equals 0. And because the action is real, those necessarily now will be complex conjugates of one another. So if I take the adjoint of one of these, I will get the other.
What's the point of the slash anyways, if you're only compressing down like two different variables? Because you went from writing three things to two things, and it doesn't seem like it's...
Yeah. Let's see, three things to two things. Yeah, that's really very true. It's you end up contracting gamma with a whole lot of different things. When you do E and M coupled to Dirac, now you have a vector potential slash. Yeah, it saves writing a bunch of little indices. You know, if you don't find that worthwhile, don't do it. You don't have to, but everybody does. You know, when you see something with a slash through it, there's a gamma on some kind of vector there. And, you know, other than looking kind of arcane and cool, yeah, you're right. You save a symbol. Big whoop. So, okay, guys, three things to two things. Oh, yes, 33% decrease. Yeah, scaling up is a good point. You know, I mean, if you're writing like 20 terms in some big, you know, Lagrangian, you know, now you've saved 20 simples. So, and you know, you can run out of Greek letters too. You know, I suppose you've done that in relativity. We're over time here, but I want to mention one thing that occurred to me while when Alex was asking about the square root of Klein-Gordon. There is a paper called The Square Root of General Relativity, where someone tries to take a kind of a spinor square root of the Einstein equation, and I think they succeed in that. I suspect they get some sort of Rorita-Schwinger field, a spin 3 halves field or something. I haven't looked at that in decades, so I don't remember what happens. But you know, you can apply that technique to more than just the Klein-Gordon equation.
Yeah, I guess that's kind of what I was wondering at, is when couldn't you do that? Because it's like,
yeah, right. Yeah, you got a second order equation, you want a first order one, so ask for it.
Yeah, if you have a complete field over your algebra, then you should always be able to find.
Yeah, I mean, you know, the linearization of the Einstein equation is like the Klein-Gordon, right? It's a wave operator. So, you know, yeah, you can write that with spinors, and you know, there may be some real benefit in doing so. Yeah, you know, people do look at those things. Okay, that brings us to the end of chapter 2 and the end of our time. But you know, we can Zoom anytime I can squeeze you in. Always happy to. Yeah, I'll try not to do many things by inspection, but
Never do.
you know, as I say, the math doesn't lie if we're careful. If we're not careful, it does often. So, but you know, be careful. We need a real action, and in the basis we chose, yeah, we don't want to have an I there. So, you know, probably when I wrote that section and put an I in, I was using the other signature for the metric or a different basis for gamma matrices. Either of those would make you stick in an I. So it always pays. And, you know, when you're writing research papers, guys, you know, do this, define your variables, define what sign you're using on the metric, you know, things like that. Because you'll learn very quickly that people who don't do that in papers will really annoy you. You know, you have to recompute the curvature tensor to figure out, you know, what sign they used for their metric, you know, things like that. And you know, it's really nice to just know up front what your notation is. So let me know if you see any inconsistencies in the notation in the book, trying to get it right. Read about canonical quantization, work exercises, compute things, get familiar with all this stuff. And we'll talk about, we'll actually quantize something on Wednesday. No class Monday, it's a holiday. So use it wisely and stay healthy, and I'll see you guys in a week. We're driving up to Montana like this afternoon, so I'd better get.
Hey,
But-
Professor, could you answer one quick question though?
Yeah, sure,
About
sure.
that equation in the right behind you with the arrow over the slash.
Uh-huh.
So wait, is this just to denote the equation right above it, right?
Yes, yeah. This means that the derivative is acting on that field.
So is this like the right hand? Is this like right hand multiplication versus left hand multiplication? Is that what we're doing? Like we've got a right hand.
Right versus left differentiation is what it is, actually, right?
Okay. Uh-huh.
So differentiate left.
Yeah. So, but this would this be like we're treating our dual basis as multiplying from the right side? I guess.
Yeah. So yeah, this is a dual vector. So that gamma mu, this thing is multiplying in, psi dagger is over here on the left, coming into that matrix.
Okay. Okay. Yeah. So this is something like then I can work with that. I can figure that out. Okay. Thank you.
Okay. Yeah. And we're going to solve this thing, in a few weeks. So, we'll have a lot more fun with Dirac stuff in a little bit, but let's do scalar fields first. Okay. Any other questions? You guys good? All right. Thumbs everywhere. See you guys in a week.
Thanks.
Have a good one. Yeah. Stay in touch if you have questions.